All right, let's start. Hello, everyone, and thank you for attending today's Applied AI Research Center's AARC Research Seminar. I am BC Min, the director of AARC. For our online attendees, please ensure your microphones are muted. If you have any questions, feel free to type them in the chat, and I will ask them on your behalf during the Q&A session. Now it's my great pleasure to introduce our speaker today, Dr. Asim Munawar from IBM. Dr. Munawar is a project lead at the IBM Watson Research Center in New York, where he's driving advancement in IBM in-house large language models, LLMs, particularly focusing on enhanced reasoning and planning capabilities. Over his 12 distinguished years at IBM Researches, he has held key roles, including manager and program director for Neurosymbolic AI. Dr. Munawar earned his PhD from Hokkaido University and has led numerous groundbreaking research initiatives in deep learning. His work centers on developing next-generation AI by integrating symbolic reasoning with machine learning techniques. With over 60 publications in leading journals and peer-reviewed conferences, Dr. Munawar is also a board member for PACT Publishing India and the National Center of Artificial Intelligence in Pakistan. Without further ado, please join me in welcoming Dr. Asim Munawar.
Yeah, thank you, BC, for a nice introduction. Thank you, everyone, for being here. I appreciate the invitation and all the arrangements you have made here for me. Thank you so much. So I'll be talking about reasoning with large language models. What can they do? What are some of the issues that we need to think about? How should I move? Okay. So first, let me get this thing out of the way. So foundation model versus LLM. So foundation models are the models that can be trained further to do some specific task, which are LLMs, okay? But recently, these two terms are used interchangeably, and that's exactly what I'll be doing. So when I say FM or foundation model or LLM, assume both of them, okay? What I'll be presenting, this will be the flow. I'll give few introductions, my motivation. Should I do
I'll
that?
take care of it.
Okay, thank you.
Sorry.
So reasoning with LLMs, can LLMs reason or not? What are the evolving trends? How to improve that, okay? And what's IBM's play in the LLM space, generative AI space? One of the things that IBM and Meta did last year is they launched AI Alliance, which basically promote open source AI development. So IBM's concept is that the AI, generative AI especially, should remain open, very transparent. Starting from the data that is used to train models to the transparency, safety aspect, everything should be in open, and that's what IBM is driving now. And let me talk about a few things that I'll not be covering today, okay? So I'll not give any final verdict, so I'll not give any solution to anything in this talk, okay? So few of the things are subjective, okay? I'll not share examples where LLMs fail. Too many examples, actually, maybe a few. So I always say this is like a celebrity gossip. A little bit is okay, but too much is not good, okay? So, and if you're even more confused after the presentation, then basically you understood it very well, okay? So that's how you should take it. So very briefly, like already BC introduced, where I did my PhD and my roles. These are my interest topics, like neurosymbolic AI. What role neurosymbolic AI can play in LLM? That's a big question. A lot of focus on this recently, and this is what luckily I found a place where neurosymbolic AI can make a difference in LLMs, and that's what I'm driving. I come from computer vision, robotics background, and few other stuff. So I'm of course interested in multimodal LLMs also. Okay. And starting from my motivation, like why I think this is an exciting time and why I like to work in this area. So because of like my childhood vision, like when I was a child, I always thought that by the time I'll grow up, these things will be taking care of everything around the house. So I used to do my daily tasks just thinking that it's just for 10 years. Like after 10 years, I'll just get one of those. It will do everything for me. This is what we have. Okay, this is the best robot we have around the house. Okay, but at least we can generate these images. So these are generated by Dolly. So at least we are there. Like we can generate these cool images now. So there is a big gap here. I think LLM is a big step. I think just like deep learning to me solved computer vision to an extent, LLM solved natural language to an extent. Okay, so we are heading there. I don't know when we'll reach. Anytime soon seems very difficult, but let's see. So what are LLMs and what they are not? I am sure that almost everyone here knows what LLMs are, what they do. I just want to give a very quick overview, and then we'll talk about the reasoning with LLMs. So it started with this transformer architecture paper, Attention is All You Need. This paper, this title also has a background, why attention is all you need versus what, okay? So there is a background there, but let's not go into that. Attention simply means to allow the network to look at all of the input data when it's generating the output. Okay, so let it focus where it wants to focus more. So here in this sentence, the animal didn't cross the street because it was too tired. So it refers to the animal. Here, the animal didn't cross because it was too wide. Here, it refers to the street. Okay, so this is self-attention. It's basically on the same sentence, which it refers to either street or animal in different circumstances. Same goes for image also. When you're generating caption for images, for Frisbee, you should focus on Frisbee more. This is how humans also do it. So attention is very helpful for the models. So LLMs are simply next token predictors. Let's say tokens are the words. Okay, next words. So they are next word predictors. Okay, that's it. Nothing more than that. They do it at amazing scale. That's what makes them very cool. But this is what they're doing in the end. So we have the encoder, which encode our input into some embedding space. Then we have a decoder, and decoder decodes and give us the next token. That's it. Okay. What's the capital of Japan? Most probably, if it's trained well enough on the right set of data, it will give us the next token, or let's say word for now, Tokyo. Okay. Self-attention is basically these three things: query, key, and value. Query, you can consider it as a question. Key is kind of the label of the column that you want to search, and value is like the actual string. If you want to make an analogy with the table, okay, this is what it is doing: query, key, and value. And this is what we are doing inside the self-attention mechanism. So in this table, if I give a query, what is the full name, it can go to the name field and fetch the name as a value. That's what's going on. And how they become Q, K, and V, because we train them to be like that. Okay, so we train these matrices WQ, WK, WV, and we train them to become key, query, and value. Okay. Is it that simple? Definitely not. There is multi-head attention, and there are multiple layers, and there are positional embeddings, and a lot of other things that are going on. But the core, this is the core. Okay, this is the core of it. So That's it. Like LLMs are next token predictors. So I was just talking at lunch also. So they work very different from humans. So humans usually, when we say something, we know what we are going to say and then we start saying it, right? LLM just start saying it. They don't know what they will say. So after LLM generate first token, if LLM was a person and you ask LLM, okay, what will be your next, so it doesn't know that until you compute it. So from a human work, because we have the world model, we know how the things are working, we know what our preferences is, our hidden motives are. LLMs don't have that. Okay, so they work they are next token predictor, nothing more, nothing less. Okay. So as I said, so I'll give a little bit of gossip, but not more. So reasoning with large language models. So recently I ran this query. I was traveling to South Africa, so I put area of South Africa versus Pakistan, and it just gives you wrong information with a lot of confidence. Okay, so it just says Pakistan is larger than South Africa, and then it gives the opposite numbers. Okay, so we have to be very careful when we talk about reasoning with LLM. So there are many potential problems. I'll give some more examples also later. Another debate that people do is whether LLMs can do reasoning or not. It's a never-ending debate, and unfortunately, Twitter just put more fuel onto that debate. Okay, so I personally think that's a completely useless debate to have. Okay, it has no meaning. The reason being, the person who are talking about in favor of LLM, they are talking about this reasoning. People who are talking against that are talking about this reasoning. Okay, so the formal reasoning is more mathematical, more symbolic. We have some guarantees. This is the reasoning that we used to do before LLMs appear. Okay, and this is natural language reasoning. This is human-like reasoning. When we ask you, why are you late? Okay, that's the kind of reasoning we are talking about here. It's very subjective, right? It's very subjective. I know people can also lie, but I hope LLMs are not doing that. But they hallucinate, we know that, right? So this is the reasoning that I will cover today. This reasoning, we are going towards that, but we are not there, okay? I'll show you some path how we can go towards this kind of reasoning with LLMs. So, and secondly, like this paper appeared early LLM era, maybe 2 years ago. So it says that reasoning is what they call emergent ability of LLM. It does not appear until certain point, and then suddenly it starts getting better very quickly, exponentially. There are papers against it also. So as I said, so this is a very well debated area. So, but anyways, it's an ability that very small models don't have for sure. Okay, after some particular number of parameters, particular amount of training, particular quality of data, it starts appearing. Okay, so that's what we call emergent ability. So let's say reasoning is an emergent ability of LLM. Okay, even with next token prediction, they can do some kind of reasoning. Okay. And another issue is that when we say reasoning, how does it differ from the knowledge? Like, what is reasoning? I think this chart differentiates reasoning from the knowledge. Okay, so knowledge is more like retrieval. It's not exact retrieval always. It's not a database search all the time. But it's, for example, if you see a wet umbrella next to your door, right? If you recognize the object, that's your knowledge, right? But humans can do more than that. If we see a wet umbrella next to the door, we understand someone came into the house just now, like, okay? So, and it's probably raining outside. That's why there is an umbrella. That's why it's wet. That's all reasoning. No one gave us that information, but we connected a lot of dots to reach that conclusion that probably someone came and they should not be putting umbrellas on the floor, but anyway. So So the difference we see here, so knowledge relies on what we already know. Reasoning tries to connect all these pieces together and make something out of it that we need, okay? So this is the difference between retrieval. Again, no one is saying LLM do exact retrieval. That's not the point here, okay? And explainability in LLM. So reasoning gives some kind of explainability also. And we, of course, like whenever there is a decision or there is an outcome, we want to know how it reached that decision, okay? And there are, again, two types of explainability when it comes to machine learning model. One is global explainability, where we understand overall what the model has learned, okay? For example, this used to be very common in convolutional neural networks, where we know what each layer is learning, okay? And local explainability. Local explainability means that for each data point, we are coming up with the explainability on how it reached that data point. So again, between these two, reasoning is more like local explainability. It's just explaining that data point. You cannot ask ChatGPT how you reason in general. The outcome will be useless, like there will be no meaning to that, okay? So local explainability is what will make sense in some cases that I'll show today. And one more concept that needs to be understood here is system 1 versus system 2, okay? This comes from this Thinking Fast and Slow book by Daniel Kahneman. And basically how humans are working are that 95% of the time we unconsciously are doing a lot of perception and decision making. We don't need to think about these decisions, okay? But we don't need to think, but on the other hand, we cannot even explain them. Okay, so let's suppose I show you a red circle, you will say a red circle, but more than that, what is color red? So we can all give RGB values, but that's meaningless, right? So there is no real explanation. We can just do stuff like 2 + 2, recognize wet umbrella, we can just do that. Around 5% of the time we are doing system 2 reasoning, okay? System 2 reasoning is where we explicitly put effort to come up with the explanation and then we reach the conclusion. For example, if I tell you to plan a vacation, that's suddenly system 2 task. First, you need to know like who is traveling, what's the budget, what's the preference, how many people, like a lot of things. So you will do like logically, you will reach a conclusion, but the good thing will be you will be able to explain your decision, okay? This was the budget, this was the weather, this was the preference, so that's why we reached this conclusion. So that's system 2 thinking, okay? It's very slow, and over time, system 2 keeps on becoming system 1. For example, when you learn how to drive, like it's system 2 task. When you learn swimming, it's system 2 task. Over time, it becomes system 1. You drive for 2 hours and you don't know like what the hell you did in the last 2 hours, so right? So this is system 2 slowly become system 1 task. And real life, like we have like both system 1, system 2 task working where like we cannot tell, like we don't need to put effort into changing our mode from system 1 to system 2. But which car should go first in here? You need to perceive many objects, that's system 1, and then you need to know the rules and you need to apply those rules. That's a system 2 task, okay? Now coming to reasoning with LLMs, okay? And the first thing that you will find is this chain of thought reasoning. This is where we can say that reasoning makes sense, okay? Reasoning with LLMs makes sense. So when we ask a question to LLM, we have two options, just like for the simplicity's sake, we have two options. Either we can ask LLM a very complex question, and we can say, give me the answer, give me the final answer. Or we can say, reason step by step and then give me the final answer, okay? So here is like a standard prompting where we show an example to LLM, some question, just the answer, okay? Here is chain of thought prompting. We give question, we give steps, we give the final answer. So this has already been shown that if we give this kind of prompts, LLM also replicates that, and LLM reason about the intermediate steps before producing the final answer. And as I said, so LLM does not have the world model. It have no concept of complexity of the algorithm, the big O notations and whatever that we study. For LLM, a complex algorithm is as easy as simple algorithm. It's just next token predictor, right? It does not take more time for complex problem, less time for easy problem, right? So, but this helps always. If it can generate, if you ask it not to give me the final answer directly, but reason about that, it takes time, generates more token, it can cost more money if you're paying for the APIs and stuff, but in the end, usually the answer is better. And this plot shows that the big circles are with chain of thought prompting, and this small circles are standard prompting, okay? The fun thing is here we gave one example. The fun thing is that we can even do zero-shot chain of thought. No, don't give any example, just tell it, think step by step, okay? If you just say that, it will generate the intermediate steps and it will come up with the final answer. And just saying that can improve the results by a big number, okay? So this is zero shot, and this is an example, like, and you will understand why it's so important. So this comes from this paper published in 2022. What is the largest state bordering Mississippi River? Okay, and it says Louisiana. If you ask it directly, it says Louisiana. Probably because it's sharing the largest border with the river, but it's not the largest state. So this is what it does when you tell it to think step by step. So first it lists the states that are bordering the river, then it gets the area of all those states, and then it's so easy to find the largest state with the largest area, and it says Minnesota, so that's the correct answer. So that's what happens when you go from simple reasoning to chain of thought reasoning. Because we clearly see that chain of thought numbers are better than simple direct prompting, we can say that LLMs are doing reasoning, okay? Again, not formal reasoning, but LLMs are doing reasoning, and it is useful, okay? But there are issues also, there are many problems. For example, this is I took it from recent paper from Microsoft called Phi 3 technical report. Okay, so it's one of the state-of-the-art paper that does reasoning very well with a smaller model, and they give results on many benchmarks. You don't need to read the numbers, but these are the kind of tasks that we evaluate these models on. Okay, graduate school grad school math problem. And for example, question answering scientific common sense question, physical interaction question answering, open book question answering. Okay, so massive multitask. So these are the kind of things that we ask these models to do, and they do them pretty well now. They do them anything better than anything we had before. They do it definitely better than non-expert human in a lot of categories, okay? So as I said, so this thing is clear that LLMs do some kind of reasoning, okay? It's usable, we can use it directly, but there are also some issues that some very serious issues that we should keep in mind, okay? So for example, this is a statement by Professor Rao. LLMs can appear to reason, but their core function is more like sophisticated pattern matching and information retrieval. Again, they are not retrieving exact information, but it's not human-like reasoning, which is true, very true, okay? Some other issues are that many people talk about some particular benchmarks, mostly math benchmarks. So LLMs, we know that these machine learning models overfit, right? So they might be overfitting to that kind of reasoning. And then many of these benchmarks were generated using some templates, okay? And they can be hacked very easily. So LLM might be learning to hack that benchmark, okay? It's also, we are never sure because they have seen internet scale data during training. It's so difficult to say that they have not seen that benchmark during training also, okay? So that's another issue. In that case, it will be more like a retrieval, not reasoning capability, okay? And as I said, so they may be exploiting these structures, hidden structures inside the data set. So in computer vision, when I used to work on computer vision, there was a paper where they differentiated between a dog and a wolf, and it was doing very well. And later they found it's just looking, if there is snow, it's probably a wolf, okay? So the image just learned, the image computer vision model just learned to do that, right? So that's what these models are also doing. So it's difficult for humans to see the pattern, but they are basically pattern matching system at amazing scale, so they can figure that out. This is a very interesting plot. This shows anything that I'm saying today will probably be wrong 2 weeks from now, okay? So if I say LLMs cannot do this kind of reasoning, after 2 weeks, maybe it's already a solved problem, okay? So this is how much time it took. I know like MNIST is the favorite data set for every like machine learning student. So it took so much time for like so many years, over a decade, to reach human capability for MNIST, okay? But look at these benchmarks, okay? So they are like, you release a benchmark today, it just need to get a little bit of traction, someone comes up and solves it, okay? So like, I don't know, like I have never seen this thing and it's like someone was talking to me recently in a meeting, and he said, this data set is very old. And I said, how old? He said, it's 2 months old, okay? So 2 months old is too old now. So that's the age we are living in. But is there data set hacking going on here? I don't know. Like we cannot say that. And I'll show you some examples why I am also a bit skeptical. But at the same time, the technology is really developing at that pace. Okay, so we should understand that. So what are the evolving trends? Like first, smaller specialized models. Okay, so use bigger models as a teacher, but train smaller models to interact with that are efficient to run, okay, economically viable to run. New architectures, of course, quantization, mixture of experts, longer context length. Longer context length is very important. I'll come to that later. Sophisticated memory mechanisms, alignment and safety. We all know RLHF. Some people say was the magic behind some models. But the 3 things that I will focus more on today is agentic behavior, okay, train time versus test time, and synthetic data, the role that synthetic data plays. And why I focus on these 3 things is, I told you, like even with next token prediction, LLM has we saw that they have ability to reason, but that's an emergent ability of LLM. Let's say that. How can we go beyond that? Okay, how do we go beyond that token prediction emergent ability of LLM? So these 3 things play a very key role there, and I'll talk about that. So how can we improve LLM on reasoning tasks by synthetic data generation. So this is a paper, easy problems that LLM get wrong. They have some interesting problem, and one of it is this: count the number of occurrences of letter L in Lollapalooza or something. So many LLMs get it wrong, and they should get it wrong. Like how can they know like how many? I don't know how that like the embedding is working, how the tokenization is working, but let's suppose it call a counter to count the letter L. It will always give you the correct answer, right? So this is what I'll talk about here, like how can we fix this kind of issues with LLM, inherent issues with LLM kind of thinking. Okay. So in our research, we mainly divide the tasks into two categories: algorithmic task and non-algorithmic tasks. Algorithmic tasks are usually where you can write a software to solve that. It's a repetitive task, okay? It needs complex computation, but it does not need a lot of world knowledge, like math problems, coding problems. On the other hand, there are non-algorithmic tasks. Non-algorithmic tasks are, for example, who was the director of some movie that was made, the famous movie that was made in 1980 something. Now that needs a lot of world knowledge, that needs a lot of interaction with the knowledge graphs or some other source, right? So these are non-algorithmic tasks, okay? So like summarization, conversation, and few others. So we split the task into these two categories, and we try to improve both categories using different methods. I'll briefly discuss few of them. So one of the thing that improves non-algorithmic tasks are knowledge graphs, okay? Knowledge graph based synthetic data generation. So we know that while during the pre-training stage of these huge models, they probably ate up the whole internet, but a lot of information is kind of encoded in these knowledge graphs that were created painfully by either manual or semi-manual involvement from human, right? So these cannot be given, these knowledge graph cannot be given to the models as it is, okay? Rather, we have tried giving knowledge graph directly during pre-training is very toxic to the model. They don't like structures. They like long stories. They don't like short to the point knowledge graphs, right? So how can we use knowledge graphs to create high quality synthetic data? This is one of the paper, again, not state of the art, but because it was one of the first one, that's why I mentioned it here. They take a knowledge graph triples and they create some question answers based on the knowledge graph. Some true false question. They also try to do multi-hop, like 2-3 hops, and then create a complex question from that multi-hop. And now we can also ask the models that this is knowledge triple, or this is few hop of knowledge triples, convert them into natural language. That usually becomes much higher quality synthetic data than asking a model directly to generate synthetic data. And another very important finding, like when this self-instruct came in early 2022, I believe, most of the people thought that creating correct answers is the actual problem, okay? But now we understand actually creating complex questions is the problem, okay? So when you create synthetic data, coming up with good questions is the real problem. Answers is not the problem. There are many ways, like there are compute intensive ways you can come up with very good answers. So knowledge graph is one way that can help you come up with very complex, diverse questions, okay? If you just keep asking the model, generate new question, you will feel they are very different, but they will be within the distribution of the main teacher model. So they will more or less, they will be the same, okay? So for diversity, you need to do something like this or some other method. So just like the last slide that helps non-algorithmic, this helps algorithmic reasoning. Okay, so if you can generate new question answer pairs. I'm not talking about the pre-training phase where you just give huge amount of time. I'm talking about the instruction fine-tuning phase where you need to give question answer pairs. Okay, so here there are tasks that can be solved algorithmically very well, and there, for example, paper like chain of code can be used where we ask the model to generate the code, we ask the model to generate chain of thought, and then we see if the answer from the code is the same as answer from the chain of thoughts. Okay, and a lot more. Like I can literally put 20 papers here. So as I said, so diversity in high quality questions are the real issue. Answers are not the issue. Okay. So this is a very famous paper, Mammoth 2 paper, where they take all the pre-trained data and filter it to produce high quality question answer pairs. Okay, so they create too many instructions. No, we don't need that amount all the time, but still, it's a very good paper. Self-discover is a very good paper, but this is more for generating answers. Okay, given the question, but of course you can ask the question also to generate the question also. And what it does is you give it all the kinds of reasoning that exist almost. Okay, and it picks up the suitable reasoning and it creates chain of thought using that kind of reasoning. For example, it can decide that, okay, this is a complex question, I need to break this into smaller problems. Okay, it can do that. It can decide that, okay, this looks like a simple COT, chain of thought question, so it generates that. And this star, it got a lot of traction. One of the reasons was that OpenAI O1 model had Q star algorithm, and many people think this is the star in the Q star algorithm. Okay, so this is a paper that iteratively come up with better rationales for given a question answer pair. Okay, there are a lot of data set where question answers, we have gold quality questions and gold quality answers with these pairs, but we don't have the intermediate steps, so we cannot train these models. So this is a paper where they come up with a iterative, although quite intensive method of coming up with new and better rationals iteratively over time. Okay, so this is a star paper. If you want to read, I'll recommend this last paper and the first one. The second one, maybe you can ignore. But with a lot of synthetic data comes a lot of filtering also. Okay, so I'm afraid, like in future, most of the data on our internet will be synthetic. Okay, so I'm really afraid, like the models trained on full synthetic data, I don't know what they will do. But it's so easy to generate synthetic data that we have to keep only the high quality data. Low quality data actually either negatively affects the model or make no difference at all. You can give as much as you want. Okay, so few common methods of filtering. Again, we'll not have time to go into the detail, but few of them we are using. So first, like go with some matrices like perplexity. Perplexity you get for free from the models. They are next token predictors. They give you the log prob of the next token that they predicted. So you can see how perplexed the model, how surprised the model is with some tokens, and you can use that to reject some data. You can ask LLM as a judge. Okay, then reward model, like outcome reward model, process reward models, or other kind of verifiers. Any trained verifiers you can use. Human evaluation, not recommended. It's very painful or very expensive. Okay, self-consistency, I'll discuss that. Search, I'll briefly discuss that. Semantic deduplication, a lot of that data looks similar, but actually it's a duplicate. Okay, so we can use some simple embedding space, like some sentence transformer embedding space, to find the data that is close to each other and remove that. PII removal, especially companies like IBM put a lot of effort in removing any personal information from these training, any copyright information, anything from even synthetic data, because somehow synthetic data might contain something that is harmful. So we take a lot of care to remove this information. So what's the future of reasoning with LLM? So it looks very fancy, right? What I told you, it looks very fancy. LLMs can do reasoning, and this I ran today morning, okay? I took the screenshot so you can also see the time that I ran this. Gemini, I asked, I have 2 bananas in the room, one fell down, how many bananas are in the room? Gemini says there is 1 banana left in the room, okay? Then I went to Claude, okay? I have 2 bananas in the room, 1 banana is still in the room, okay? So you see the conflict between like amazing data sets, and then you ask this question and they fail, right? So you get confused, like what is going on? ChatGPT got it right, and you still have 2 bananas in the room because 1 fell down but didn't leave the room. And I think I know why, because I asked this question to ChatGPT many times, and I believe strongly that this is not innocent smile, this is a sarcastic smile. See, I got this, finally I got this right, okay, so this is sarcastic smile. So, but I always, I don't know why, but this was the first question I asked ChatGPT when ChatGPT appeared. Because I work in reasoning space, this is the first question I asked. It got it wrong so many times, but finally it starts giving it correct answer. Okay. So there is a big contrast between what is going on, like benchmark versus real world problems. So this is, I used to follow his books for a long time because of his work on RL also. But what he says, and I fully agree with him, is that what humans try to do is to build all the knowledge into their agents, okay? And temporarily it's okay, but in the long run it's never a good strategy, okay? And eventually we have to do the search and learning needs to go hand in hand together. So I totally understand what he's saying. I couldn't agree more with him. And that's what's happening with LLM also. We thought that put everything there, one model to rule them all, one model done, we all go home, that's it. But that's not how the world works. So how do we go beyond what LLMs can do? So the first thing that comes to mind is agents. Agent is a word that keeps changing its meaning. I think it's a word that always do justice to the word. I think it keeps up with the era. There were RL agents, there were probably agents before that also, and now the agents are used for this LLM kind of agentic systems. And in agentic system, we allow the LLM to generate an output, critique on its own output, use other tools to do something. Even it can use other LLM to critique or verify or maybe interact with the tools. Okay, so especially the software engineering agents have shown incredible progress. So software engineering agents can solve software bugs just by looking at the GitHub issues. It's an incredible success story there. So a good agent needs to be good at reasoning, planning, and tool calling. And you see, like immediately when you say tool calling, now that condition of emergent ability doesn't apply anymore. Now it can run a query, it can fetch the information. Anything that is missing, it can fetch from something that is more symbolic. Okay, so to me, they are converting into neuro-symbolic systems now, where some things are symbolic, some things are neural, and they work together. So one thing that my team is doing is how we can improve these LLMs on tool calling. Again, they are good at tool calling, but a lot of room for improvement there. Okay, so a few things that we are doing are here, like API detection, slot filling, like what function to call, what parameters to send, in what sequence, if they are nested or not, if there are dependencies or not, and so on and so forth. RAG, like do we need to retrieve something and then generate the outcome based on that, and so on and so forth. Okay, so this is one area that we work on. I'll briefly just skip over that. So we have some good results, and you see our models are like Granite 20 billion. Any model that comes from IBM becomes open source from day one. Okay, so IBM time series models, IBM function calling models, IBM RAG models, even the main LLM reasoning models, they're all available on Hugging Face for free. So we have one of the best open source function calling model. Okay, so that the agentic thing was one thing to go beyond the emergent ability of LLMs, but the next discussion that is happening as we talk here is training versus inference time scaling. Okay, do we spend a lot of time on training the models, or we spend more time on inference time? Just like O1 preview does, they call it it's thinking. We know it's not thinking, it's just generating a lot of tokens, and it does not share all those tokens with us. So it takes a long time to generate the output for us. And this is the next thing that is going on right now in the LLM space. So train time compute, how it affects the accuracy, and test time compute, how it can affect the accuracy. You see, it's pretty similar. You can spend a lot more time on inference, and the accuracy can improve. We know, like, test time compute costs money. So this is the money we are paying for every token generated, every million token generated is this one. So we care a lot more about that. We want to reduce that, but still, this scale similar to train time compute. So in training, we have few things that we can do. We can have better data, more diverse data, more difficult data, quality data. Okay, and how we do that is synthetic data generation. Now it's all synthetic. Even if we take a human annotated set, we usually pass it through a synthetic data generator. Okay, to modify it to LLM's liking. Architecture, filtering, human in the loop, reward models, alignment. So these are a few things we can do to improve the training time. Okay. What can we do to train to improve the test time? Okay. So search algorithms, for example, MCTS, Monte Carlo tree search kind of algorithm, better and long chain of thoughts. I'll discuss this a little bit. Agentic behavior, tool calling. These are all test time things that we can do. ORM and PRM, okay, they can be used there also, but process reward models usually can verify each step. Automatic verifier, self-correction. So these are all test time things that we can do. So there is a strong, right now, very focused research going on which one is better, or how to kind of trade off between both. So I think I'll skip that. So, for example, given this example, which one is heavier, 1 kg of cotton or 1 kg of steel? So it's an interesting question for maybe second grade or first grade, elementary school kid. But GPT-O1 preview answered it correctly, but it took 22 seconds. And I don't know how many tokens it generated to reach this conclusion, right? So no one wants to pay money for this kind of question, right? So the goal is that we do a lot of this compute, but in the end, we generate high quality data from this, and we feed into training the model, okay? So again, the story goes back to synthetic data generation. even at test time, if you're computing a lot, why not keep all that data and train your model to do better next time? Okay. These are like trade-off curve. We can skip that. So open, what open is doing, no one knows. They did not open it, so we don't know what's going on. But few keywords from their blog are large-scale reinforcement learning algorithm teaches model how to think using its chain of thought in a highly data-efficient process. Okay, so first of all, they're doing some kind of reinforcement learning. Secondly, at the inference time, it's only chain of thoughts. Okay, and third, it's some data-efficient training process. And from search and neural, like search plus neural model, we know we have some examples from past, like AlphaGo or something, where they do a lot of search and they train the model. And of course, at inference time, it does not do search, right? But for training, it can play like against itself or other models, and then it can train. So we have some very good hints here. So RL needs some kind of reward signals. That reward signal should come from some reward model or process reward model in this case, because process reward model give you a reward for each step. Okay. Inference time is nothing but long chain of thoughts where it comes up with the solution, and then it basically says, okay, no, this doesn't look good. It goes back. Okay. So it seems like it's running some loop algorithm, but it's actually just a very long chain of thought. Okay. And training some high quality data, mostly probably by self, by playing with itself, like in this conversation scenario. So going beyond chain of thought. So we know simple prompting, input, output, chain of thought, we give some input, we have some chains, and then we reach the output. Self-consistency, that I believe like is the best way to generate a reasonable quality data or outcome, is by run several chain of thoughts and do a majority voting on which answer is the correct. In math, this works like magic. Okay. You can run like 20, 30 if you want, but of course it takes compute. So self-consistency can improve, generate multiple thoughts, pick up the best one. But if you want to go beyond this, you need a verifier. Okay. And this is like from the early experiments from OpenAI, where they intuitively, it's difficult to understand, because what they are doing is they have a generator. Okay, generator so they train a generator by giving the question and the solution. Okay, now they label those solutions if they are good solutions or bad solutions, and then they train a verifier on that. Give question answer pair, and the verifier will tell you whether it's a good question answer pair or bad. Okay, it will give some kind of rating. So intuitively, it's difficult to understand like why this is so important, like why reward models are so important. Reward models are trained on this kind of data where we have good quality question answer pair, we have bad quality question. It learns somehow to differentiate between those two. But what the original self-instruct paper said is that for humans, it's very easy to differentiate bad from a good one, but it's very difficult to give absolute number to something. Okay, so you can just say that, okay, I like this reply more than this reply, but if I tell you give me from 0 to 10 scale, give me some kind of rating, it's so difficult for us to. And probably same thing happens for the model also. So verifiers are amazing at telling which is better, which is wrong. Okay. So here we see, like, if we just do fine tuning at 175 billion, this is what happens. If we use a verifier at the test time, suddenly it becomes much better. And advanced chain of thought using verifiers, like We have tree of thought, where we generate many different chains of thought, and we kind of reject something, and then we go back, we traverse another route, and so on and so forth. We have best of n, where we generate many chains of thought, and then we get the best. But you see, here we need a verifier. We need a verifier that tells us, okay, this is a good chain of thought, this is not a good thought, okay, so on and so forth. So the verifier can suddenly open a lot more venues for us. So this is a Monte Carlo roll-up. Like, you can, for example, is this good or not? Do a Monte Carlo tree search. Just go all the, like, of course you cannot do infinite, but use some kind of algorithm to see how many of them reach a successful outcome, how many of them fails, okay? And you can assign some number. And this is what we want to do. We want chain of thoughts, verifiable chain of thoughts to train our model, so that our model, most of the time, it gives a good output, okay? So we need these complex chain of thoughts. So this is a simple, like, maximum likelihood problem. It's combinatorial, it's interactable, so we need approximations always. But this is what ultimately we are doing. We are training a model that generates this kind of chain of thoughts, but most of the time it should be generating the correct ones. Sometimes it can generate wrong also. So this is like coming to almost the end of my talk. So we need long chain of thoughts that O1 reasoning is generating, okay? And there are many ways to do that that people are kind of talking about. No one knows exactly what's going on under the hood. But long self-constructing correcting chain of thought is, for example, like, this is a tree of thought where we just stop. Like, if we reach a wrong thought, we just stop there. In self-correcting chain of thought, like, we connect it with other thoughts, and we kind of like go to the wrong place and then correct yourself and then come here, okay? So if we create this kind of data, a lot of this kind of chain of thought data, and we train the model somehow, the model will learn this ability of doing some chain of thought. If it makes a mistake, correcting itself and then fixing it. Believe me, it's not easy to train this model. Like, I don't know how they did it. That's still a question mark to me. But yeah, ultimately it should just ignore this as a noise. But this is one of the things that comes to mind when we talk about test time. Making models able to do test time compute scaling. So was O1 the holy grail? Is everything solved now? The answer, sadly, is always no. Okay, so this DeepSeek, I believe it's a company from China. They showed like they can, with more tokens, they can literally go a lot better than O1. This is O1 accuracy. Okay. There is another very interesting paper that appeared 11th November, which basically, so they update model parameters temporarily to improve the inference. Like, it's amazing. So a lot of things are, like, I can put a few more here. So a lot of things are going on to go beyond O1. O1, again, as I said, so on benchmarks it looks very good. On real world problem, as I said, so which is heavier, this or that, it can take time. So you feel that it's definitely not the holy grail. It hasn't solved everything. So we still have a job, thankfully. And last, like, what's IBM doing in this space? So this is a question that many people may not know the answer to. So IBM is building a series of models called granite models. Just like some companies picked cameloids name, llamas and alpacas. And so IBM decided to pick stones. So granite, and we will see some more stone names in future also, okay? So, and two models, like granite code model is already there, granite language model is already there, and they perform like within their size category, they perform very, very well. Okay, so these are Granite 8 billion model compared to Llama 8 billion model. So they are, and the good thing is that they are also available in very like 400 million range, 800 million range, 2 billion range. So even they can run on a laptop processor. And you can see in benchmarks, reasoning benchmarks, they're doing state of the art or exceeding that. So these are the results on some benchmarks, but I'll share the slides with you. You can forward it to people. And this Instruct Lab, this is a way to create more synthetic data in a more scalable way that we are developing at IBM and Red Hat. Okay, I'll skip that. I want to go to conclusion and then open to question answer. So in conclusion, so LLMs have shown remarkable reasoning capabilities, but there are some serious limitations. So just like the 1 banana, 2 banana example that I showed you, you see suddenly the benchmark is doing 90% and you ask a question, it's not able to answer very simple. So you start questioning yourself literally. So LLMs are not used as next token predictors anymore. So they are becoming neurosymbolic systems. So we cannot argue anymore that pure neural system cannot do so and so. Okay, so they are not pure neural systems anymore. They involve search, they involve tools, they involve verification. So ongoing research, very high quality synthetic data is a very good research topic. Agentic behavior with external tools, how to improve that. Software engineering, they found a very sweet spot where GitHub issues, people define GitHub issues in a reasonable manner they can pick. So anything else you can find is a very good area to work. Inference versus train time compute. Amazing, this is very interesting. RLHF, how we can reduce human feedback and go towards AI feedback is again very interesting area to focus on. And future, like how I believe things will go in, like neurosymbolic AI, like all the methods that 2 years ago people thought that are dead will come back. Architectural changes, okay. Knowledge and world model, like how knowledge graphs and world models can be built by these large language model and preferably shared between each other. That would be amazing. Better benchmarks that are more focused on real world problem, not template generated math problems. So true explainability, not asking the model what you think about something, okay, and not made up story. So like truly you understand that, okay, this parameter and this thing fired and this thing fired, okay, so this is the path. These are the rules that were applied to come to this conclusion. That's the explainability that we would expect in future. And thank you. So there are many ways to connect with me. Do connect with me, okay? Thank you.
Right, thank you, Dr. Munawar, for the great, informative, and also very insightful presentation. We now have time for questions. So for those who are in the room, when speaking, please use the microphone since we have some online attendees, and also this is being recorded. Any questions?
Hi, Dr. Munawar, great talk.
Hi, thank you.
My question is on the quality of data that is being used to generate foundation models or LLMs. So the way I understand, foundation models are built on any kind of data and they don't have very high accuracy or performance, but then they are tailored for specific tasks. So what you said that the data quality plays a huge role, right? So would there ever be a shift toward training foundation models with highly curated data? Right now, because big companies, they have all the compute, they can do it, right? But data quality is really important. That is my first question. And my second question was on, I'm forgetting that. I'll come back to it.
Sure. So very good question. So I agree that big companies have a lot of compute power, okay? But the thing that goes to our advantage is that all that noisy training happens during pre-training phase. okay? And I don't think anyone in a university, or even when we deal with the model, we don't talk about pre-training. There is a team at IBM that do pre-training. We talk about instruction fine-tuning, okay? So at pre-training, the quality matters, but not to that extent. At pre-training, we are just telling the model to predict the next token. That's it, okay? It's not able to follow instructions at that point. That's what we call base models. The next step is instruction fine-tuning, okay? Instruction fine-tuning, we have seen that the quality makes or breaks the model, okay? If you can have like gold quality data, the model will perform very well. It can overfit, so don't get me wrong, it can overfit. So models do like a little bit of noise, right? So, but the good thing is that even 100K examples are enough to train instruction fine-tune a model for your particular problem, okay? So 100K on single GPU, you can easily train 8 billion model without any issues within few hours. That's it, okay? You can train get a base model trained on your high quality data.
I remembered my second question. So what comprises data quality then? Right? So what is the notion of data quality? Is it specific to specific tasks, or is there something like completeness, diversity, coverage? What do we look for in data quality?
So I think you have also trained a lot of models.
No,
probably.
I have not. I work in data quality.
Yeah, but very good question again. So we also struggle with this question. What is high quality data? Okay, so a simple definition would be high quality data is anything that improves the model. Okay, but you cannot do a lot of experiments to see if your data is improving the model or not. Okay, so with very few okay, let me talk about one more thing. So data mixtures. Now you have many different data sources from many different places. What ratios should they be combined in? That's a huge hyperparameter. But let's suppose you have figured that out. What is high quality data now? So we short of training a lot of models and seeing what the data, which part of data should I keep or not. So we want some kind of matrices that can tell us something about the quality of data. And the two things that work reasonably well are perplexity, okay? So you can look at how perplexed your model is, like how surprised your model is to see some data. The tricky part is if your model is too surprised to see some data, it can either be that that data is very good, it surprised your model, means your model was not able to guess. It can be that that data is noise. It's useless data. Okay, so it's a double-edged sword. So for that, perplexity plus LLM is a judge. Okay, ask if you want 8 billion model, but you have access to a bigger model. You can ask a bigger model to tell you something about the quality of the data. Companies like IBM, we cannot use proprietary models to evaluate our data. So copyright and all that issues. For research purposes, maybe you can do, I don't know. But for research, maybe you can use a very good model and you can ask it to tell you something about. So perplexity plus they work very well together.
Okay. Yeah. Thank you.
Yeah. So we come back.
So my question is about the increased accuracy or quality of responses when giving chain of thought prompts. You used this as an example of how the LLMs may be producing a kind of informal reasoning, and I'm wondering what your thoughts are about the difference between informal reasoning and simply having more tokens with which to arrive at a better answer because the response format is longer.
So the question is that why do they do good?
Like if we are asking them to give us a chain of thought reasoning, we're basically giving them permission to give us more tokens, and so they're having more time to arrive at an answer that makes sense.
No, very, very good question, but I think that's not the case. We are like giving time to them to think in that conventional sense does not mean anything, because LLMs are not.
That's not what I meant either. No, I don't think that they're thinking at all. No, I meant that, is it reasoning to simply have more tokens in the chain of prediction? Like, this is what I'm not understanding.
Oh, so longer chain of thoughts
Yes.
will be better than shorter chain of thought.
Yeah, so if we don't ask them a chain of thought prompt and they give us the wrong answer, we ask them a chain of thought prompt and they give us the correct answer. Is that reasoning, or is it just that they had more steps?
No, sorry.
Yeah.
I get your question. It's a very good question. I think it's related to the last thing that I explained, very long coherent chain of thoughts, okay? So if we allow the model to critique on its own chain of thought, then it makes sense, okay? If, for example, somehow the model understand within chain of thought that, okay, I came up with a solution, this is not good, I need to revisit. It can be agentic behavior, it can be built in within the chain of thought training itself, okay? If we allow the model to go back and redo something based on the outcome, it makes sense. Very often what happens is we ask model generate code for something, and if the model has access to, let's suppose, Python interpreter, it can run that code. It runs that code, it runs into some error, and it says, I got this error, I need to go back and fix it. In that sense, it makes sense. Otherwise, if we don't allow the model to rethink, it will not help. Longer chain of thoughts will not help at all. Yeah. Okay. But training these models are very difficult. Like on longer chain of thoughts, it's very difficult to train these models. So.
Hi, thank you, Asim. So my question was slightly more on the strategic side of building these models. And then what I wanted to ask was, how are the timelines? Like, you're working for IBM and let's say you're working on another version of Graphite. Like, what's the timeline or what's the process of developing these models? Like, how do you guys set your milestones? I was just curious to know more about that, because I know a lot of probably years went into building the initial one. So I was just more curious about that side of building these models.
Yeah, thank you. Interesting question. That's the whole industry. The whole industry is doing what IBM is doing these days. So IBM works a little different from others. Like when we release a model, we make it super transparent what data was used. So it takes a lot of time in data preparation. Okay, so what happened when this LLM thing started after ChatGPT is IBM decided to train their own models. And initially, the first question was like where to get data and the data that is okay to use, right? So, but once you get the data, and IBM of course had a lot of experience from like previous, not at that scale, but once you have the data, it's a simple, like you can literally do calculation that how much time will it take to train my model. Let's suppose you have internet scale data, you want to run 5 epochs. You can easily tell my model will be trained in 3 months. The only issue is not a matter of hours or weeks anymore. It's months that it needs to train on 100 GPUs, on 200 GPU, 400. I don't know how much they use. So once you get everything right, but getting everything right is an experience. Like, as I said, so now you have 5 different data sources, or let's suppose 500 different data. What's the mixture? What's the right mixture? That's an experience. That's either you do it algorithmically or you learn over time how to do that. So that we are still in the process of learning. But once we decide the data, we can predict that, okay, after 2 months our model will be ready. And now we are at a stage where we can predict very accurately when our models will be ready, next generation models will be ready. Yeah. Thank you.
Hi. So my name is Nabin, and I wanted to ask about like ML is more about like data and architecture both, right? Like previously before CNN, like once CNN came, like there was more like a lot of innovation once CNN came, and like previously we used to do like feed-forward neural networks. So instead of doing more things on data, like doing like generating synthetic data, can we not work on more like generating synthetic architectures that the model can work on? And wouldn't that be like better advancement than generating data?
So again, like all questions are very good. So before this LLM started, so there was a lot of research going on auto AI and auto ML, and every company proposed different names for it. And one of the things was to find architectures that are good. So search on architectures that are good, how many layers should there be. But now they have become so expensive to train even a single model. You cannot do search anymore, okay? So I do strongly believe more powerful architectures will appear, okay? But right now, letting a model do its own search in architecture, it's too expensive. Like we cannot do that. As I said, so one architecture takes few months to train. Imagine asking it to try 1,000 architectures, okay? It's just does not make any economic sense right now. Okay, so the only thing that we can do right now is probably improve the data, and at the same time, like the architectures are getting better. The memory, flash attention, too, and so they are getting better, but we are not close to automatic search on architecture right now. Yeah.
Right. Hi, Dr. Munawar. Thank you for the great talk.
Thank you.
My question is about what you were talking about regarding the data filtering. So my question is, how do these data filtering techniques, like you mentioned, for example, LLM as judge or human eval, how do those work at scale and in really specialized domains? Like, for example, if we're talking about the medical domain and you want to generate some synthetic data for that, then after you generate that, ideally or traditionally, what would happen is you'd have some domain experts like doctors review it. But if we are trying to train these really large scale models, the size of the data set is so massive where it's not practical to have these human domain experts do it. So then if you look at LLMs as judges to try to evaluate this, that could work, but because it's such a sensitive topic, especially the medical domain, how do we go about doing that data filtering?
So from sensitive point of view, let's forget about the confidentiality and that part,
right?
Okay, because that is very difficult to address. I'm not an expert there, but how LLMs, like if there is absolutely no way to evaluate your outcome, unfortunately you're stuck with human experts. Okay, that's the only way. Now, as I said, so what these big models did in the beginning, like Claude basically did a lot of RLHF, RL with human feedback, okay? So they pay like literally crazy amount of money to human annotators, to companies like Scale.ai, and they pay literally crazy amount of money to get the data annotated. How the annotation works for reinforcement learning is they just ask, is this better or this? Which one is better? Okay. A is greater than B. Yeah. They don't ask them to give a absolute number, because humans are not good at giving absolute numbers. I don't know how teachers grade the papers, because they should not be. Now coming to think, if we make an analogy, it's very difficult to do. Humans are not good at that. But anyways, so unfortunately, we have seen that with, for example, chemistry problems. It's so difficult to find any reasonable judge that we have to go back to human experts. The thing is, how can we reduce that? Yeah. Okay, how can we reduce that? So for that, we have some mechanisms like iterative mechanism. For example, Llama, what Llama did in Llama 3 paper is, instead of doing one iteration of reinforcement learning, they did 5, okay? And so they do the training, then they basically build a reward model, ask the model to generate a lot of solution, reject a lot of them based on the reward model, train again, then build the next reward model by annotating more data, like ask the model to generate many questions, ask humans question answer pair, ask humans to evaluate, again update the reward model, do the RL again. Okay, so you have to do this iterative.
So RLHF is an important part of this.
It becomes very important if there is no other way to find this verifier.
Because you need some way to trust that the verification from the LLM is correct.
We need to do that. Yeah.
Okay.
So if it's very unique domain that is not well researched in these famous data sets and benchmarks, we are stuck with human experts.
Okay, got it.
But it's painful. Like literally last week, I don't know why I started that. I verified few question answers. Literally, you want to kill yourself after verifying like 10, 20, 30 long chain of thoughts. You literally. So it's very bad.
I was recently just working on a course project using like VLMs for this medical domain question answering thing, and I had to generate some synthetic data. But my problem was, even if I asked GPT-4 to give me like 500 new questions, I don't know if the outputs are actually correct or not, and I don't have like the medical domain to verify. So that's kind of where it came from.
An interesting area that what we were doing is that we have knowledge graphs which we can trust. Generating, first of all, synthetic data from thin air is can be like very problematic. But if you give a part of knowledge graph and ask the data to LLM to generate the data based on that part of knowledge graph, it usually does a much better job. And if you can somehow create a cross verifier that comes back, okay, to verify if the original facts of the knowledge graph are there in your generating, you can be pretty sure that, okay, this synthetic data covered everything that was in the original knowledge graph. So few think that cyclic verifier can help a little bit.
Okay.
Maybe not too much.
Thank you.
Okay.
So we have some questions from the online attendees. So let me read it out. Thank you for the very interesting and insightful talk. Could you talk more about the potential biases in LLM-based reasoning and ways to address them?
So potential biases
in LLM reasoning.
Yeah. So this is a general, I believe it's a very relevant question to generative AI era. But I think it's not related to reasoning in particular, like it's there in generative AI overall, like the issue of biases. In reasoning, there is a bias, for example, there is no solution. Reasoning does not provide a solution to biases, okay? So to be very frank. And there is a more bias toward more complex problems, okay? So that's why somehow LLM, even if you ask a very simple question, it gives a very complex answer to that, okay? So that kind of biases are there, but unfortunately, can we talk to those people like who are remote or no?
I think they can hear.
But can they? Can they clarify? Can you clarify, please, your question?
Yeah, sorry, I wasn't very clear in my question. So I was thinking more in terms of the biases that could happen in the human reasoning process. For example, confirmation biases or cognitive biases. Do you think such biases would also occur in LLM-based reasoning process?
Okay, yeah. Now I understand well. Yes, they do. They do appear, and the thing that how we are solving those are by creating multiple verifiers. For example, we, instead of having one reward model that just tell us whether something is good or bad, we have multiple reward models. One that tells us whether it is safe or not. One that tells us whether it is in this domain or not. Okay. One that tells us whether it's coherent or not. So you can build more reward models, and you can be sure, a little bit more sure, that there will be less bias in that. So that's the way we are doing it. But I'm not expert in this area, so maybe there are more methods to doing that.
Okay, Dean, are you still there? Maybe you can unmute your microphone and then ask your question to Dr. Munawar.
Sure, can you guys hear me?
Yes.
Okay, yeah, thanks. So yeah, great talk, thank you. I come from the library world, and we've been looking at and creating linked open metadata and RDF triple stores, looking at the semantic web for about probably 20 years, I would say. And those type of data graphs seeking like very high quality training data. Have you seen experience of training on linked open data from the web, depending upon like what you're trying to train for? Your one knowledge graph slide just kind of reminded me of the RDF kind of subject, predicate, object formula. And in the library world, we've been very careful to make sure all of our metadata is accurate and correct. And I'm just curious, like if you have any experience of hearing where that kind of quality data has been used to ensure a higher quality model.
Yes, so good question. So we are using that kind of data. And the thing is that, as I said during my presentation, so if you give that data as it is during pre-training or post-training, it kills the model. Okay, these models don't like templated, very structured data. They like long stories. Okay, so if you want to give a RDF triple or knowledge triple, you convert it into a sentence and you give it to the model, and the model will learn whatever you wanted it to learn. So, but if you give the whole store in the original form, these models will not be able to learn anything useful out of that. So one thing that we are doing is that we create comparative questions out of these knowledge graph. For example, by date of births of certain people, by dates of events that happened in the world. We can do some temporal reasoning. It's very easy to get data from these knowledge graphs instead of making those dates up and making up the events. That does not make any sense. Okay, so we get these things from the knowledge graphs, and then we ask LLMs to generate data based on this part of the knowledge graph, and that's worked pretty well. And that will help with non-algorithmic part of the LLM usually, because it will increase its knowledge. It will not allow it to do better algorithms. Okay, so it will solve a part of reasoning. Yes.
That actually made me think of another question when you were talking. It makes sense, right? Because they are like word based, and they like the wordy things. But
yes.
Do you think would there be any possibility of creating a system which would be like somehow able to do that learning just using the graph structure?
There is research going on that part also, but I'm not too familiar with that. But the thing is that because during pre-training, their strength comes from the internet scale data that they saw at pre-training, and that was all in textual form. So they cannot be very good at graphs. Okay, they were trained to be good at text. So that's the issue. They are trained to be good at next text token prediction. But there is research. I do know there is research going on, because there is always, I always say it's a parallel community that always talks more about graphs within the ML community, and I believe there is some work going on. I saw a paper recently, maybe I can forward it later if I can find it again. Okay. But that's interesting research topic. For research topic, definitely it's very interesting.
Okay, all right. Thank you, Dr. Munawar, again for sharing your work with us today. And let's give him a big round of applause.
Thank you.
And also thank you everyone, whether you are joining us online or in person, for attending talk today. So now this concludes our seminar. Thank you, and we look forward to seeing you at our next seminar, which is in January 2025. Thank you.